Folks, hello and welcome to Topic 6. We're going to move into Chapter 11 this week, and I've got a couple problems teed up for us to get us started in this material. So starting with problem number 11 from Chapter 11, we've got a manufacturing problem here. Hart Manufacturing makes 3 products. Each product requires manufacturing operations in 3 departments, A, B, and C. The labor hour requirements by department are as follows. So what we've got here, again, we're making 3 separate products that require manufacturing from 3 different departments. And what we have here are the hours that are required for each product by each department. And then it goes further to say that there is a maximum of 450 labor hours available in Department A, 350 hours available in Department B, and 50 hours available in Department C. Finally, the contributions by profit, $25 for product 1, $28 for product 2, and $30 for product 3. So all of that information has been adapted over here in a very simple LP model. This one is quite simple for us. We're maximizing the profit. I've got our old friend here, the sum product formula in here to compute the sum product of the decision variables and the profit contributions. And then similarly, I'm using the sum product of the coefficients, which effectively are the labor times for each labor area for each product made, sum product, and then I have the right-hand side constraints. So this is a very simple model. No need to go through this one any further. But it's important to set that up as we go through and look at the second half of this. It says, after evaluating the solution obtained in Part B, we'll consider this our Part B. One of the production supervisors noted that production setup costs had not been taken into account. She noted that setup costs are $400 for product 1, $550 for product 2, and $600 for product 3. So what we're saying is here, this model does not take into account a setup cost for, it looks like for some sort of machinery if we're making product 1, product 2, or product 3, and that needs to be considered. Based on these costs here, notice that as I have adapted the initial problem to consider the setup costs, notice that first of all, notice that I've added 3 new variables or 3 new decision variables. C1, C2, and C3, which are the costs respectively for product 1, product 2, and product 3. And notice that since I'm maximizing the objective function, the coefficients associated with C1, C2, and C3 are the negatives of the dollar values given. So if I am making product 1, I am going to subtract $400 from the overall profit because I have a setup cost and so on and so forth. For the other 3 products. You'll also notice that I've adapted the constraints area down here to include the setup costs for product 1, setup costs for product 2, setup costs for product 3, which are my C1, C2, C3. Now, the question is, how do we incorporate this into the model? And we've talked about mixed integer linear programming problems this week where you have some decision variables that can be anything greater than or equal to 0. And then we have some situations where some of the decision variables have to be very discrete values. In this case, we're going to introduce what we call a binary variable, saying that C1, C2, and C3 only have 2 options in terms of their values in the optimal solution. They can be either 0 or they can be equal to 1. If it's 0, it would mean that, for example, if C1 ends up being 0, that would say that product 1 was not manufactured. If C1 is equal to 1, that means we have an optimal solution that considers product 1 being manufactured. So what I have done here is I want to work on the relationship between P1 and C1, and then you can figure this out for the other 3 or the other 2 based on the way I've got the coefficient set up here. So first of all, note that it goes further to say here that for this production cycle, it says management also stated that we could not consider making more than 175 units of product 1. So as I look at P1, the decision variable, P1 has to be a value between 0 and 175. Then I say further, if P1 is equal to 0, meaning I don't make any of product 1, then the cost associated, or the setup cost C1, will also be equal to 0. But if P2 is greater than 0, meaning I make some of product 1, then C1 has to be equal to 1. That way I pick up the cost of the setup of the machinery to make product 1. So that this little algebra setup here, just make sure you think through that one carefully, and then the rest of this will make sense. The way that I take this into account from a programming standpoint, I'm saying that P1 has to be less than or equal to 175 times C1. And when I move the 175C to the left-hand side by subtracting it, this is what I'm left with. Now let me make sure that everybody understands this. Let's take a little time to understand this. If I don't make P1, that means that P1 is equal to 0. So if P1 is 0, 0 minus 175C is going to be equal to 0, because if you look at this, if you look at these three terms and their coefficients, because the objective function is being maximized, Excel does not want to pick up any of these costs. So Excel is going to keep this at 0 by default in order to not pick up the cost. So if P1 happens to be 0, then 175 times C1 is going to be 0, and 0 minus 0 is less than 0. However, if P1, let's say for example, P1 is 1, meaning we make one of these products, the only way for the left-hand side to be less than or equal to 0 is if C1 becomes 1. So if you say that P1 is equal to 1, then 175 minus C1 has to become minus 175 in order to make the left-hand side less than 0. And because remember, C1 can only be 0 or 1, right? So when you go through and solve this, I want to make sure that we have agreement on the products and the costs. So let me set this up. I don't know, I might already have this solved for you. I do. I can just do it real quick. So I want to minimize my objective function here. I want to maximize using these decision variables. Make sure you get all 6 of them. And let's see, the first thing I say is that F20 through H20, which is C1, C2, C3, those have to be binary. They have to be either 0 or 1. And then the final constraint here, I27, let's see, 27 through 32, those computed values have to be less than or equal to the right-hand side values. So let me go through and solve this. And let's make sure that we have agreement here. So since P1 is being made, then C1 has to be 1, and it is, right? So I'm picking up this cost of the setup. P2 is being made, so C2 is being picked up as a cost as well. So we're subtracting 550. And notice here that P3 is not being made. And so since P3 is not being made, notice that the coefficient of minus 600 is 0. So this cost is not being considered as well. So very quickly, let's see, 25 times 100 is 2,500. 28 times 100 is 2,800. So that's 5,300. 5,300 minus 950 is how we're getting the 4,350. And so I think the key point here is, and as you go through these problems this week where you have this mixed integer situation, where you're going to have some number of decision variables that are binary. I hope this one. I'm gonna do this. By the way, I'm gonna do this in 2 separate videos this week. I don't like to make these any more than about 10 or 15 minutes long, so I'll do this first one, and then I will record a second for problem 1123. But again, what I want to make sure that everybody does is make sure that this is clear in your mind, right? The constraints on P1 and what happens to P1 depending on its value, and then make sure that this is makes sense to you as well. And like I said, I did this for P1, but once this is satisfied in your mind, you can go down here and understand these the setup for product 2 and product 3. Let's see, based on the given fact that only 150 units of product 2 can be made and only 140 units of product 3 can be made. All right, so let's see, I think that clears us up for problem 11. Like I said, I'm going to do these in 2 separate videos this week. So I will pause here and I will post this, and then I'll do a second for 1123. Thanks.